Good evening, everyone, and welcome to North Jersey Astronomical Group's monthly meeting. Today, we have Dr. Phil Erickson, director of MIT's Haystack Observatory, join us to share his groundbreaking work in black hole imaging. Also delve into the intricacies of the Event Horizon Telescope and some of its recent discovery. Dr. Erickson is the director of the Haystack Observatory and principal research scientist. He also holds a PhD in space plasma physics and oversees cutting-edge research in radio astronomy, conducting fundamental research for a variety of sponsors in the field of radio astronomy, geospace, near-Earth space, and very long baseline interferometry and geodesy. Dr. Erickson also holds a amateur radio license and is on the Science Observatory board for the Ham Radio Citizen Science Initiative. So we look forward to hearing his presentation today. I, for one, am excited about it. I also want to state that following the presentation, we'll be transitioning into the business portion of our meeting, and we would like our online club members to stay with us for the second half of tonight's meeting. So with that, Dr. Erickson, if you want to go on ahead and share your presentation.
Excellent. Before I do that, thanks very much for the opportunity. I'm going to make a slight correction to the introduction. I am not a radio astronomer, nor do I play one on television, as the old phrase goes. I am actually, my background is in geospace physics, so the physics of the upper atmosphere, the charged part, the ionosphere, the neutral part, the thermosphere, and then the magnetosphere, which is farther out in nearer space, the part that's still controlled by the Earth's magnetic field. But as the director of an observatory that does a bunch of different things, I have very kindly prevailed upon my colleague Kazuo Akiyama, who is in fact a black hole imaging expert, to give me a bunch of slides, which I will attempt to, without some errors, go through, but the topic will stay the same. So
well, I do apologize for mine.
Oh, no. It was wasn't you. I just wanted to set the record straight here. And that you have to know who you're getting. But in any case, I've been doing radio science in one form or another since 11 years old, when I wish you could see it, because there's a vacuum tube receiver over my shoulder. That was the thing that I started with in radio, listening to shortwave broadcasts from Deutsche Welle and Vatican Radio and Radio Moscow, which was a little interesting thing in the 1970s in the Cold War. In any case, that led me to the sort of professional radio science career that I've had. And I've since January, I've been the director here at Haystack, which means that my scope has expanded a bit. So what I thought I would do, and by the way, my friend Mary Lou, I very much appreciate you inviting me to give this, and you'll have to tell me how it went later. So let me start to share the slides here, and we'll go from there and see how we do. All right, let's see if I can make sure that I push the right buttons here. Okay, so now I've got this, and I'm going to go for full screen, and I want you to make sure that you can actually still hear me and that the slides are full screen. Is that the case?
Yes.
Great.
Yep.
Okay, so I'll start out for a little bit by, who am I and why am I here? I mentioned that I'm the director of this thing called Haystack Observatory. We are located in Westford, Massachusetts, which is along Route 495, kind of tucked below the southern New Hampshire border, but well away from the MIT main campus in Cambridge, Massachusetts. We've been here since the 1950s, and we are a radio observatory. So we are basically doing the same electromagnetic observations that you would do with, say, optical telescopes, except we use really, really long wavelengths compared to those, or really, really low frequencies. But many of the things that you do with a radio telescope, you might are familiar. You can see in the background, there's some fairly large parabolic dishes. The largest antennas we have on site are a 68-meter or 220-foot vertical antenna that's down at 440 megahertz frequencies. Next to it in the background there is a 150-foot fully, or 46-meter diameter fully steerable antenna. Inside the radome that you see in the foreground is a 37-meter extremely precision surface radio antenna that is used to do satellite imaging, as well as doing observations of distant objects for radio astronomy purposes. It will work at millimeter waves. There's nothing else on the planet even remotely close to it. So we have a lot of different frequencies and a lot of wavelengths that we use, but it's all radio science for us in one form or another. We have about 1,300 acres, or 526 hectares, if you like metric units for acreage, here in the Westford, Massachusetts area on the top of a small hill. And you can see a bunch of different names there for the various pieces of the observatory on top of our small hill. I'm talking to you from the building under the 37-meter antenna and the radome. Radome is something that is transparent to radio waves mostly, but is opaque to optical radiation, which is why it looks white. And this is not only a radio observatory where we don't transmit and we passively observe other objects like things in the universe that are emitting radio waves, but we also sometimes make our own radio waves in radar form, where we bounce those waves off something and then use that to remotely detect its properties. For example, in the upper atmosphere, density, velocity, composition, and temperature. So with all of these different facilities, we actually kind of are split into two pieces. The observatory is run by the Massachusetts Institute of Technology, and I've reported to the vice president for research at MIT, which means I get to do unclassified scientific research, and we get to talk to folks like the club here about what we do. We administer the entire 1,300-acre site. We operate like a campus department, except for none of us are faculty. We are all soft money, meaning that we have to sing for our supper in terms of getting grants. On the right-hand side, MIT has concentrated all of its classified research into something called Lincoln Laboratory, which is in Lexington, Massachusetts, which is halfway between here and the MIT campus in Cambridge. That's all Department of Defense sponsored research. They share space and facilities here with the observatory, and they have a number of radars that have been operating for a very long time. The first radar on the hill detected Sputnik 1 2 days after it was launched on October 4th, 1957. We ranged it on October 6th, 1957. We were the first thing in the world to actively range that particular satellite. So we've been doing that part for a long time. And finally, before we get into black holes, just to tell you what we do, radio science, we are a place that concentrates on both science and technology. So the tools that you see on the right-hand side of the screen are the ways that we do the science on the left-hand side of the screen. And you can see we cover a number of different disciplines for both passive and active techniques. Tonight, we're going to be concentrating on the red parts, something called very long baseline interferometry to study distant astronomical objects, which are very, very small in angular size. Talk a little bit about how small they are in a bit. And that's applied to the science of radio astronomy. But as I mentioned, my background is in atmospheric science and geodesy, which is the science of Earth orientation and rotation, which is where you turn the problem around and you say that star is fixed and I'm going to watch the telescopes wander around on the planet. And you can figure out things like how fast the Earth is spinning. The continents, are the continents moving away from each other? They are. And other things like that. So we do a number of different things, and there was no way I could even hope to describe all of them in tonight. So we're going to concentrate on a pretty, exciting subject, which is we're going to talk about imaging black holes at radio frequencies. This is something called the Event Horizon Telescope. So I am a reporter. I am not a radio astronomer. My colleague Kazuo Akiyama gets all the credits for these slides because he's a real radio astronomer. I just get to hang around with him in the hallway. And so we're going to be talking about those donut images, the orange donuts that you see right there, kind of how the telescope works at radio frequencies and the latest findings. I have erred on the side in this presentation of selecting the slides from Kazu that maybe there's some of them are a little heavier on technical detail and some of them a little bit lighter. Hopefully that means that there's a little something for everybody in here. But feel free, if you can call out and ask me a question as we're going along, that will be fine. It's a little harder to do that over Zoom, but give it a try. Okay, so we're talking about a black hole, very exotic object, and you want to actually figure out the environment around the black hole. How are you going to do that? Well, black holes have been around for a very long time. The concept, at least. But yes, the black hole itself has been around for many, 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 many years. But the idea is, what's the concept? Well, this may be familiar to you from undergraduate physics. This is how you determine how to get the rocket off the ground. There's SpaceX launching something. And how do you get away from, for example, the Earth's gravitational well? Well, that's the formula for the escape velocity from a star, for example. If you know the universal gravitational constant, you know the mass of the thing you're trying to get away from, you know that that's the velocity you have to use, which is a function of how far away you are from the center of mass of the object. Okay, that's pretty fundamental. And we have the mass of the star, there's the M. We have the radius of the star, there's R. So those two things tell us how fast we have to go to get away from it. Well, what happens if you keep turning the crank? And like John Mitchell in 1783 says, how big, how massive does the thing have to be where the gravitational tug is so strong that even light can't escape? Well, if you take a look there and you take the bottom part and you square both sides, you get V squared on the left-hand side and you get 2gm over R. And I'm going to make that R as R sub S. That's the Schwarzschild radius. That is the point at which the thing is so massive that nothing can escape it, not even light. So if you can see, if you flip that equation around, you notice the speed of light has now appeared. That's the C. And so that is the formula for something called the Schwarzschild radius. Now, this is a theoretical construct, okay? So let's put some numbers on it. For example, there's 350 grams of water. All right. If you take 350 grams of water, what's the Schwarzschild radius of 350 grams of water? In other words, how much would you have to condense that thing to be a point where it's got such a powerful tug that even light can't escape? 10 to the minus 24th centimeters. Okay, we're already into, orders of magnitude that you can't really estimate, especially since the atom is about 10 to the minus 8th centimeters, and the electron is not electron. Electron is 10 to the minus 16 centimeters. So you're probably not going to make a black hole out of your can of Down East ale if you could compress it into minus something that is 10 to the 16th times smaller than an atom, or 10 to the 8th times smaller than an electron. Probably not going to happen. So the radius of a black hole is therefore proportional to its mass from that formula we had. So let's, again, put some more numbers on it to give you an idea, to try to get some ability to get your mind around this. Let's take the planet Earth. Anybody know what the radius of the planet Earth is? If you guessed 63 and 28 kilometers, you're right. So let's make it 6,000 kilometers radius. Let's take the mass of the Earth, which is 6 times 10 to the minus 24th kilograms. So how big is the radius of a black hole with the mass of an Earth? About a sugar cube, 1 centimeter. Take all the mass of the Earth, crunch it down to a centimeter size. Remember that can of lager? That's about 10 centimeters size. There's a classroom, 10 meters. There's a baseball stadium, 100 meters. So you can see the sizes that we're talking about here. Large masses condensed to really small things if you want to get the matter down to small enough sizes that you're capturing everything, including light. Okay, there's the centimeter. All right, so that's the Earth, right? Well, let's try the sun. How big is the sun? Well, the radius is about 7 times 10 to the 5th kilometers, so almost a megameter, almost 1 million kilometers in radius. Its mass is 6 orders of magnitude bigger than the Earth, or about 2 times 10 to the 30th kilograms. So how big a black hole would that make if you take the mass of the sun and crunch it down to a size where light can't escape? Well, there's that baseball stadium again. This is essentially the distance between Haystack and a very good ice cream place called Kimball's, about 3 kilometers from here. This is the distance between Haystack and MIT, about 30 kilometers. And it turns out that the black hole would be about this, something of the mass of the sun, and the radius of the sun would be about the distance between here and our favorite ice cream place, about 3 kilometers. So that's the size of the object. So you can see an enormous amount of mass, a big radius crunches down to something pretty small. So observing these black holes is already going to be, I think you can see, quite a challenge. There's the fiducial sort of size of that Schwarzschild radius. So the fellow on the top that you might recognize and some other people kept on going with this concept of black holes. Turns out they are the densest object in the universe for a given mass. There's something called the event horizon is the region from which no escape is possible. Eventually things fall in and go somewhere else in the universe. And there's a whole lecture that I'm not qualified to give about where they go. This was predicted by our friend Albert on the top there by his general relativity equation in 1915 and 1916. That you can predict what the size of that event horizon is. And again, there's a whole lecture in there that I will not give, but that's the formula for how to calculate what the parameters of that black hole would be. And this fellow, there's Carl Schwarzschild, the Schwarzschild radius. He was the one that solved that and said, oh, well, this is that radius beyond which nothing is going to escape, not even light, nothing. It took until 2020 that we can, there's the 2020 Nobel Prize in Physics, Roger Penrose and Stephen Hawking. We recognize Stephen Hawking on the right-hand side there. There was a mathematical proof that this can be formed in the universe, but it took a while beyond the Schwarzschild sort of theoretical predictions and Einstein. So what about a black hole? Well, there's a thing about, does a black hole have hair? What's its shape? It turns out that if you work through the physics, the black hole has to have three quantities. It's got a mass, it probably is spinning, or maybe not, and it's got some kind of a charge. These are fundamental properties of the black hole that fall out of the theoretical equations. And it turns out if you do a nice scaling argument, the Schwarzschild radius works out to be 2.95 kilometers, or about 3 kilometers, times the ratio of the mass of the object to a solar mass. And you saw that a little bit earlier because I said, well, the sun crunches down to about 3 kilometers. You can see it right there. So as the mass gets bigger, the radius gets bigger. Let's look at a black hole that's fed by the amount of mass in a star, stellar mass. This is formed by the gravitational collapse of massive stars, bigger than 30 times the mass of our sun. The mass is, by the time you collapse and everything kind of settles down and you form the black hole, you're talking about a mass of several times the mass of the sun to 10 times the mass of the sun. That's this particular gravitational collapse mechanism. And it turns out that for supermassive black holes, there happens to be one in the center of our galaxy. That is a place called it is in a group named close to the radio star Sagittarius A star. How do we know there's a black hole there? Well, before anybody was crazy enough to think about trying to image it, the people at the Keck Center at UCLA did a very simple experiment. Well, simple. They did radio astronomy observations and they measured the location of various radio emitting stars, and they just measured it once every 6 months for about 25 years. And what I'm going to show you now is a little movie of the way those stars are moving. If I can get it going here. Yeah. Something is massive enough at the center of our galaxy to pull these stars out of their orbits. So we had indirect evidence that there was something very massive there, and the theoretical construct was, well, it's probably a black hole. You could weigh the black hole by knowing something about the mass of the stars going by it, and actually then trying to figure out how big would that black hole have to be for the gravitational pull to be enough to actually warp these things out of their orbit. And it turns out that, sure enough, the Nobel Prize in Physics in 2020 went to Roger Penrose, Reinhard Genzel, and Andrea Ghez, basically that says general relativity predicts black hole formation, that eventually these black holes will form. Things will collapse in and on themselves, usually at the center of galaxies. And Reinhard and Andrea basically got the Nobel Prize for the maps you just saw, which is the discovery that there's one at the center of our own galaxy. And there's Andrea and Reinhard on the right-hand side. So the interesting thing is they are literally the most energetic power plants known in nature. So for example, you have a ball, its gravitational energy to be released is about that big. Again, we're talking about now just not just balls, but things the size of stars. So there's the table. A nuclear power plant is about 0.1% efficient at releasing energy if you look at E over mc squared. The sun, it's an overachiever, so it's about 0.7% efficient. A black hole, because it is releasing gravitational energy, is 6 to 42% efficient compared to the 100%, which is extracting every last drop of energy from a unit of mass. These are incredibly efficient power plants, which is another reason why they are thought to play a role in almost all the formation of things like galaxies. Now, for the supermassive black holes, some of them are extremely active. Look at Cygnus there. The yellow is the optical, the red is radial emission, and the blue is X-rays. You probably know that X-rays are a pretty powerful photon. Look at all the energy flying off that thing, which you can't see because it's very tiny, but it's in the center of Cygnus A. So we think Cygnus A also has a black hole in it. So we have both emission, which is radiative energy, like the little space heater that I hope you're not running in your house, because when it falls over, it starts fires. And then there's the jet, which is kinetic energy. So some of that energy isn't just released as emission, it's actually blowing material out of the center of the black hole if it gets too close, and is forming a jet which swirls out from the center. So we have both radiative energy and kinetic energy released at unbelievable levels by the environment around the black hole. And it turns out that there's, if I zoom in literally almost 1 trillion times into the center of that, this is the simulation of what we think is happening at the center of Cygnus A. Look at all that material flying out. That's the kinetic energy. But not only is it radiating, it's also just spewing out energy in jets. But there is a gap. I've just been talking about supermassive black holes. There's probably a whole zoo of different kinds of black holes there. So do intermediate mass black holes exist, and how do the supermassive black holes evolve? So there's your stellar mass black holes. That's a few times 10 times mass of sun. That's kind of the intermediate mass black hole. And then there's the supermassive black hole, like the one at the center of our galaxy, which is literally 1 million to 10 billion times the mass of our sun. Such a gravitational tug that it's actually ripping material around and doing things like forming galactic structure. So we'd like to figure out, is there anything in the middle? You know, intermediate is between the left and the right. One of the things is you might recognize the 2017 Nobel Prize in Physics, which is the LIGO discovery of gravitational waves, which actually are generated by ripples in gravity that are generated when two black holes merge. They're so powerful and there's so much energy efficient released that you actually end up warping gravity. And that was the incredibly brilliant LIGO experiment, which, as I'm sure a whole nother lecture by other people far more qualified than I am, but it's a whole nother fascinating subject, and it's right. But at the heart of the gravitational wave are two things like two black holes colliding with one another, both attracting and creating all sorts of chaos. But how does the black hole in the sky look to us? Well, light is getting bent around these black holes. And so what we really see is kind of like a ring, because inside that ring, the light is being bent away from any light coming from behind the black hole is actually being bent around the black hole. And I'll have some more animations of that in a little bit. So we have to figure out, what does the thing on the sky look like to us? How big is it? Can we measure it? And oops, I think I went the wrong way. I'm still going the wrong way. Hold on. And so, for example, there's light. Oh, the light can't really go through the black. It has to go around the black hole. So if you take the light from a bunch of different stars, you're going to end up with a ring. You're not, or a sort of toroid. When we look at the black hole edge on, you're not going to see light in the middle because that light is being bent by the gravitational distortion that's happening from the black hole. Keep going the wrong way. Pardon me. Come on. Hold on a second. So what you get is a shadow that is created by the black hole. And that happens to be in a place where there happens to be dense stellar concentrations somewhere nearby the black hole that can create light that's actually then be getting wrapped around the black hole, for example. So you end up with this, the famous orange donut. And we're going to spend a little more time figuring out how you measure that. But the scale, the incredibly tiny size of that black hole, think about how far away it is. It might be 25, if it's in the center of our galaxy, it's 25,000 light years away. If it's another one that we're gonna talk about, which is in the galaxy M87, that's, you know, much farther away than that. And yet the black hole is a very small, so it's got a very small angular size. So there's a couple of animations in here that are intended to give you a little bit of an idea about that. So here is a simulation. Here you are at this is the Atacama Desert in Chile. And we're going to look up at the constellations and we're going to go try to find the environment around the black hole. So we're zooming in and we're not even close yet. Oh, something's appearing. There's the heart of a particular galaxy that we're trying to look at. And if you keep on going in, you go past the dust clouds, you'll begin to notice that there's a jet coming out of there. There's the kinetic emission. And somewhere down in the heart of that very thing, keep going, keep going, keep going. There it is. There's the environment around that black hole, that singularity in space and time. So once again, by measuring the shadow of the black hole, you can actually weigh the black hole, because we know from Schwarzschild's work that if you know the universal gravitational constant and you know you can measure somehow the radius, you can weigh that black hole. Again, knowing the speed of light, assuming that general relativity holds. And you go back a century, because it's going back to about the time of Schwarzschild and Hilbert. Some of you may recognize the Hilbert transform. And so that's the same Hilbert. So by measuring that black part, the shadow of the black hole, you can try to attempt to determine what the Schwarzschild radius is. And it turns out that the shadow of that black hole, if you think about how light is being bent around the black hole, is about 5.2 times the Schwarzschild radius. So you're going to see a toroid with a hole in it. If you can measure the diameter of the hole, you can figure out what the mass of the black hole is. So you have a scale now that you can weigh the black hole. So just another animation here, because we like animations. This again are all of the photons of light in the neighborhood of the black hole. And sure enough, there they all are, getting bent around by the black hole. We're trying to observe. We're over there to the right. And then if you look edge on, that's what we're going to see. And as you keep on filling that in with more and more photons that get bent, this is actually in simulation what we're trying to measure. This is the image. And some people are very disappointed by this image, saying, it's really fuzzy. Why can't you make it detailed and looked at like that really cool simulation? Well, that would be great if we had a lot more telescopes. And I'll kind of tell you about that in a little bit. So if I'm going to measure a black hole, what are the easiest ones to measure? Which are the ones that have the largest angular size? The two that the Event Horizon Telescope Project concentrate on are the two top ones. The first one is in the center of our galaxy, It's got 4 million solar masses. It's very close. It's only 8 milliparsecs. It's small. It's 10 micro arc seconds. And I'll have a little chart about angular sizes in a little bit. And then one that's very, very much farther away, it's 16 MPC away from us, long, long way away from us. But it's 1,000 times heavier. It's actually 6.5 billion solar masses. But it appears about the same angular size to us, farther away, but it's actually bigger because its mass is bigger. And so there were two attractive targets to start with. So how do you measure something like that? Well, those of you who have played with telescopes may realize that the telescope diameter is inversely proportional to the resolution of the object that you're trying to measure. So a bigger telescope, and especially one that has more wavelengths across it, is going to give you a better angular resolution. But we got to get to micro arc seconds. A second is a 60th of a minute. A minute is a 60th of a degree. So a arc second is a 3600th of 1 degree, and we've got to go 1,000,000 times smaller than that. These things are really tiny. So what do? I use radio waves that I can phase up. So not only using amplitude, but also phase. And I make a telescope the size of the planet. So I literally have telescopes that are as far apart as I can get on the Earth. And I combine all of them, and I do different combinations of what we call baselines. Each one of those forms an interferometer arm. And by a worldwide collaboration where you actually coherently record signals at all these telescopes with really good clocks, like hydrogen masers that are accurate to 1 part in 10 to the 15th, so they lose a second every 2 million years, you can phase up all those telescopes to actually measure something that's like a telescope, the diameter of the planet, where the distance between each telescope is measured in giga wavelengths, like 10 to the 9th wavelengths, but which it's a really lousy mirror because we only have a few little dots on the mirror. But the resolution is determined by the greatest distance between any of those 2 points. And so here's a little animation of the telescopes and all the different baselines that they have. So as the planet rotates, each telescope begins to see the black hole and can form coherent baselines or interferometer arms with the other telescopes. And there is the black hole, and the blue is the resolution of that planet-sized telescope at radio frequencies. That's the Event Horizon Telescope. And you can see that the resolution is a little better than the Event Horizon, which is good because that means we can measure it. That's Sagittarius A star, the one at the center of our galaxy. That's a few million solar masses. And this is the farther away run, M87, much more massive, but farther away. And it's about the same angular size. So that's why these two were picked. And this is just another nice image sequence showing you there's, again, one of the telescope arrays in one location. And this is if that was trying to measure something on the moon, this is the size of the thing that you'd have to try to measure. Keep going, keep going. There's some craters, there's some individual kinds of things, rocks, and there's our little chocolate donut that we're trying to measure on the surface of the moon. So that's the angular size. And again, we all know our protractor. 1/60th is an arc minute of 1 degree. The moon, as you might well know, is about half a degree or 30 arc minutes. 60th of that is an arc second. 1,000th of that is a milliarc second. Another 1,000th is a micro arc second. And that's what we're trying to measure, is an orange on the moon from the surface of the Earth. So it takes a lot of careful work to make sure that you can measure that. The other analogy is that if you stood on a hill about 25 miles or maybe 40 kilometers here from Haystack, your job is to resolve half the size of the hair, one of the hairs on my head. So it's incredibly challenging. but it can be done. And so the Event Horizon Telescope itself, here's some nice pretty pictures of some of the antennas used. This is the ERAM 30-meter telescope in Spain. This is ALMA on a mountaintop in Chile, 57 antennas phased up to act like one. The large millimeter telescope in Mexico. These are all at millimeter waves. This is the sub-millimeter telescope out in Arizona. This is the JCMT in Hawaii, the sub-millimeter array on a mountaintop in Hawaii. This is at the South Pole. It takes a long time to get the data back from the South Pole, so you got to put it on a ship. All of these telescopes and more are combined. We kind of borrow the telescopes every time there's an observing session and then give them back for other uses. This does not happen with one person or a couple of people. This is a picture of the Event Horizon Telescope collaborative, some people. It took 350 people across 120 institutes and 21 countries from all continents to make this measurement, all working together. This is the primary example of something that is truly international, truly global, truly requires that everybody work together, regardless of where they're coming from. And the collaboration is particularly proud of that achievement. So this is the international collaboration. And just to show you that just here at Haystack, this is some of the people that were involved in our little part in forming the image that we're going to talk about a little bit more. So just some of our researchers. Now, how do we get from observations from all of these telescopes to the images? Well, what we do is on the left, we have all of the telescopes. They're getting waves and they're arriving at different telescopes at different times. They have really good clocks. Each one has a digital recorder. We literally fly the hard disks to here at Haystack. We play them back from a very fast device into a very fast correlator, lots of add and multiplies. We calibrate, we find the weak signals hiding in the correlator output, we reject noise, and then we actually do image reconstruction where we synthesize an image, make it compatible with the few points we're able to measure on the image, and then come up with a result. Because we're very poorly sampling that image. That image is actually a simulated image that is consistent with the measurements that we make. In terms of image reduction, this is incredibly reductive. We start out with literally tens of petabytes of signals from all of these telescopes. By the time we correlate them, we've thrown away 3 orders of magnitude. We're down to terabytes. We calibrate the images. Now we've thrown another factor of 1 million away, down to megabytes. And finally, the final image is a few tens of kilobytes. 12 orders of magnitude in data reduction. And my colleagues, Kazuo Akiyama, the fellow who provided me all of these slides, is on the left there, along with my colleague Jeff Crew and Vincent Fish, in front of our very fast correlator with all those data recorders. And he's holding 8 terabytes times 8 hard drives. That's 64 terabytes, and there are 92 of those for each image we try to make. So this is a lot of data. So what do we do when we've got all of this data and we punch it through this correlation process? Well, what we do is we're trying to make that image on the left-hand side. We use a clever trick. We basically do that in the frequency domain, a 2-dimensional frequency domain on the sky. I'm not going to go through the details there, but the point is that we're trying to make that image and we are sampling it only on a limited set of points on that particular image, or equivalently, the spatial image gets transformed into a Fourier image, and you can see that those little red diagrams there. Sometimes we sample some parts of it more than others, depending on where the planet is oriented when we're trying to look at the black hole and taking data. So in reality, we're trying to sample the thing in the middle with a sparse set of points. How do we do that? Well, we take advantage of the fact that the Earth rotates, which is very convenient. And so what happens is, as say the black hole in the galaxy, the Messier object M87, as the Earth rotates, for example, the coverage you'll see starts to fill up as we add more telescopes. You can see that we're starting to get new data that samples different scale sizes in the image. As we go, we start to be able to make an image that's consistent with that data that you see forming kind of on the third box there as the planet rotates. There's an enormous amount of mathematics behind this because you're trying to do something that's, you're trying to make kind of as much as you can out of the sparse data that you have available. And the way we do that is we have a couple of different ways to do this. I'm not going to go into the details. The traditional way of doing it is on the left, which is basically you take an image, you project it onto the telescopes, and you come up with that thing labeled Y, and then you try to invert the process and adjust the image until you close the loop that best matches the current image. And you notice also it says guidance from knowledgeable user there. There's a lot of art to doing that. So you don't want to really rely on that as your only way you're doing it. The other way to do it is to forward model it. And if anybody knows Bayesian statistics, that's what you're doing on the right-hand side, which is you're taking the image that you hope to get on the bottom with the question mark, and you're pouring it forward through the measurement equation from where all your telescopes are located. And then on the top, you have a candidate image. You do that same pouring forward, and then you form a conditional probability. And you adjust things until you get, again, the two things to match. That's an inspired by Bayesian technique of optimization. And you get to deal with all sorts of fun things like thermal noise, phase errors in your measurement, systematic errors, amplitude errors. All of that is the wonderful job of the calibration process. And then you also get to deal with other things like you want to make sure that the image isn't negative, sparse, smoothness, information entropy. You throw the kitchen sink at this, everything you possibly can get. And then you try to come up with that's, by the way, anybody who knows Bayesian posterior kind of thing, that's a very familiar equation. If anybody has ever looked at that, this is just, again, make an image that's consistent with the observations that you've made. Now, there are challenges to this. The bottom 5 are different methods, all of which would yield the same observations that we make, but all of which have slightly different features. And your job is, which one is most representative of the data you've got? Well, you've got an ambiguity. Those 5 at the bottom are all, you see at the top there, the top left-hand side is the simulated actual image. The one on the right is the blurred image that our telescope affords us, but it could also be the one that's on the bottom, 1 or 2 or 3 or 4 or 5. The question is, how do you tell? It's kind of like trying to measure the snowman. The snowman gets really blurred, and then your 5 guesses on what the snowman looks like are at the bottom. So how do you differentiate all of these? Is there a right answer? Are you just fooling yourselves and there's no black hole image at all? So the way this team did this was really clever. They split the researchers into 4 imaging teams, one in the Americas, one a global team from US, Japan, and Netherlands, one from cross-Atlantic, US, Spain, Germany, and Finland, and one from East Asia, Korea, Japan, and Taiwan. You handed them all identical data, and you didn't allow them to talk to one another. And they each went off with a different technique and made their idea of what they thought the best image was, given the data that had been measured by the telescopes. The teams on the left were using new techniques like Bayesian stuff. The ones on the right were using traditional techniques. 7 weeks later, the teams met for the first time in a room. And there's the picture. Katie Bowman is the one who led the collaboration. They're all clapping because the 4 teams came up with images that were within 10% of one another. At that point, people thought, okay, we actually think we have something. this was the most rigorous process they could think of to make sure that we weren't fooling ourselves. So after that had happened, within 10%, the images, there's some detail differences, as you can see, but all of them had nearly exactly the same radius. And that's the Event Horizon Telescope. So we got to April 11th of 2017, or 2018, I remember, I can't remember. I think it was 2018, actually 2019, excuse me. And there's, for example, the details of 3 different ones. And there was a fiducial image that got created, which is, okay, we're going to make the image, we're going to combine all these, tweak them up, and that is the image of M87, which is the farthest one away, but it's also the most stable because it's the heaviest. So the thing doesn't change as the planet is rotating and you're trying to observe it. So that's the first that one was done. Not the closest one, but the one that was farthest away, but was much heavier and therefore is much more stable. So what does that radius tell us? Well, there were previous measurements from things like those star orbits that said that the mass of that black hole was about 6.2 billion times the mass of the sun. This is the one in M87. And there was a measurement by looking at the way gas was sort of swirling around in the neighborhood of the black hole, not really close, but somewhere in the neighborhood. And that was, okay, it's about 3.5 billion masses of sun. So we're within a factor of 2. The prediction would be that the black hole radius would be, there's 5.2, there's the Schwarzschild radius. So we'll put a little bit of uncertainty on it. You know, there's anywhere between 4.84 and 5.2 Schwarzschild radii. There is, by the way, so that is the inner ring, which actually has something called a wormhole, which is a really exotic place where things leave the universe in one place and appear in another one. And if you keep on going, that is the Schwarzschild radius where even general relativity doesn't work anymore, and we don't know what happens. So inside that ring, that's where things get really, really bizarre. But did we measure the yellow ring according to those other masses? Okay, so if we measured, and sure enough, the independent masses mean that the stellar mass agreed, the gas mass did not, and the black hole radius matched the yellow ring. It's not a wormhole. It's not a naked singularity. The material around the black hole, which is glowing like crazy, is consistent with the separate rough estimate of the stellar mass. So that must be a 6.5 billion solar mass black hole. Quite cool. And I won't go through that. The deviation from that prediction is within 10%. So Einstein was vindicated yet again. There are no significant deviations from general relativity within 5 Schwarzschild radius of a supermassive black hole with over 1 billion times the mass of the sun. This, by the way, you're seeing is the highest fidelity image that humanity has ever produced, given its extreme small angular size. And so, once again, to give you some scale, there's the sun, there's the orbit of Pluto, there is where Voyager 1 is, and that's the scale we're talking about. Still very, very massive, very large from our puny solar system, but unbelievably small in the cosmic sort of, scale. So, check. The size of the shadow agrees, allows for only small corrections from general relativity. And since this is an international collaboration, I am probably understating it when I said that it perhaps made a little bit of a splash. These are just some of the front pages of the original black hole image. And then, of course, people had fun with it. There's Homer Simpson eating the black hole donut. There's the Eye of Sauron below, Homer Simpson. There's some BBC Doctor Who image. So people had lots of fun. By the way, there's a TARDIS. They're flying into the ring of the black hole. And then someone fuzzed a picture of a bagel. So this has been obviously a lot of fun. So after all of that happened, people were still working on incredibly detailed general relativity. This is called MHD, is magnetohydrodynamics. This is what happens to plasma, for example, in matter when it's in the neighborhood of these incredible gravitational forces. And so that little sort of circular spinning thing is the simulation of what was actually the black hole. You'll notice that it's got spiral arms and it's got lots of details, but we still can't hope to measure those details given the fact that we're stuck to the planet. More about that a little bit later. And it was measured several times in the 2017, and the images were quite similar. So that's good. I will not. And then it was also measured in multiple times. The 2017 was the first black hole image. And so you could actually go back to earlier times when the array was sparser. And there is 2009, 2011, 2012, 2013, 17, 18, and then 18 and 21. And it's pretty stable. That's the M87, the one that's really supermassive and stable. So where do we go from here? Well, we not only can measure the sort of emission, if you will, the amplitude of the emission, but if we're really good because we have radio photons, we can measure the polarization of the ring, which tells you something even more interesting about the environment around the black hole. It can tell you something about its magnetic field. And I will talk about that now. So you have this black hole. We're on the right-hand side trying to get an image.
The plasma swirling around a black hole has magnetic fields threaded throughout. If the magnetic fields are weak, the plasma
You guys probably couldn't hear the audio, right? Is that correct? Yeah. Oh, you could. Okay. Well, let me just let it run.
The plasma swirling around a black hole has magnetic fields threaded throughout. If the magnetic fields are weak, the plasma drags them into a circular pattern. The plasma produces light waves that oscillate perpendicular to the magnetic fields, resulting in this polarization pattern shown here using white tick marks. On the other hand, extremely strong magnetic fields resist the plasma's motion and straighten out like spokes on a wheel. When we produce a black hole image, the polarized light waves now exhibit a different pattern. Finally, if the magnetic field strength falls somewhere in between these extremes, it generates a spiraling pattern. While in reality, many factors might affect the polarization of light, this intermediate case roughly resembles the Event Horizon Telescope's observations. By analyzing these tick marks, we can learn about the geometry and strength of the mysterious magnetic fields that surround black holes.
So you can learn yet more about this extreme environment and the fact that it's highly magnetized. In fact, what we really care about is the accretion flow. People have called black holes messy eaters. They basically are eating all the matter in their neighborhood, causing that matter to swirl around the drain, if you will, and the matter gets super hot. And then some of it gets ejected out the ends into these jets. That's the kinetic flow. And of course, some of it is radiating energy, and that's the radio emission we can see. So what can you do with this? You can start figuring out more about the black hole. We've already talked about the fact that you can figure out the black hole mass, and you can also tell something about the fact, is it spinning? You can also figure out how fast it's eating, what the mass accretion rate is. And then by doing polarization, you can figure out what the magnetic flux is. What's the magnetic environment around this particular black hole? Higher magnetization, and I won't no way we're going through the details, but the point is, as the black hole is highly magnetized, the fields are more coherent, less random. They look kind of like poloidal. They've got that north-south structure, and they will produce a stronger jet. All of this walks into cosmology about the effects that the black hole is having on mass in its neighborhood and how that's leading to some of the structure in the galaxy that the black hole is at the center of. So the people who study how galaxies evolve are very interested in the zoo of black holes out there. What are their different characteristics and how are they forming the environment around them? So those are the first M87 results, right? Where are we? Just to summarize, Einstein has passed the most strict test of general relativity that has yet been done in one of the universe's most strong gravitational field, and gravitational and general relativity still worked. The strongest evidence yet for the presence of a supermassive black hole at the center of M87. We know that that central black hole is most likely spinning from some of the details of the structure of that image. And an active galactic nuclei and an associated jet are really powered by this engine at the center of that galaxy, which is a supermassive black hole. Furthermore, the stellar dynamical mass is correct. It agrees with another measurement that says it must be about 6.5 billion masses. And it's actually more, if you keep measuring it, there are slight day-to-day variations, and there's also variations over multi-years when you look right into that horizon scale. And the magnetic fields are coherent. They actually form a very good picture of the magnetic field environment. And in fact, the immediate vicinity of the central black hole is strongly magnetized. So one of the reasons why this was also significant is that this is really a new era of black hole astrophysics. This is how you start delving into the details of black holes beyond the point where you're just watching these stars and you're kind of weighing the black hole, but you're not figuring out all this other information that we have managed to get if you do all this imaging just correctly. I'm going to skip this part. Now, another kind of image there's going to show you here. That's what the galaxy looks like in optical. That's not what it looks like in radio. If I zoom in and I zoom in here, and this is at radio wavelengths, not optical wavelengths, and I zoom in again to the neighborhood of the object at the center of it, look at all the hot material coming out of there and emitting in radio frequencies. We're still not far in enough. Here we go. Something is appearing, and there is the environment around the black hole. So, why did we pick the M87 one first and leave the one near us for the second one? Because of this. That's the simulation of Sagittarius. It actually changes on day-to-day timescales. Imagine taking a picture of a toddler who keeps running around as you're trying to get them to stay still long enough to snap a picture of them. This required an entirely different set of imaging algorithms that could take the prior constraint that the thing was actually changing as you tried to image it. So the black hole at the center of our galaxy has this challenge, and it also has the challenge that there's a lot of scattering from some of the other objects like dust and other kinds of gas near the center of the galaxy, which means that it looks like that frosted window pane on the right-hand side. So you had to be able to figure out how to unblur the image. Much larger, and you'll notice that it took 3 more years of work to produce an image of Sagittarius A star in the center of our galaxy because of all of these particular challenges. And it ended up looking like that. It's, again, 50 micro arc seconds, or about 5 Schwarzschild radii. and again, agrees very well with general relativity's indication of what the size of that particular event horizon should be. It's not a wormhole. It's bigger than the wormhole. It's not a naked singularity. So it passed the same tests as M87, and that general relativity was working. I'm going to skip this part. And so now we have two images. One on the left is M87, and the one on the right is Sagittarius A star. So where do we go beyond this? Well, we'd like to add more resolution to that image, right? We know we would be able to image it, but it's still somewhat blurry. So what do? Well, we'd like to add more telescopes. Like somewhere in the middle of this decade, we'd like to add even more telescopes to the array that images the Event Horizon telescopes. They all have to have really, really fast recorders. They have to have very, very good hydrogen maser quality clocks. And a lot of them are in fairly inaccessible places like tops of mountains, which has its own set of challenges. So in 2018, the Green Bank Large Telescope was being added, and that has been done. The recorders got faster. In 2020, just about in time for the pandemic, the GLT became official, and NOEMA over in Europe and Kit Peak over in California were added to the array. In 2023, we added the Owens Valley Radio Observatory in California. That's the thing called Karma there. We added a frequency at 345 gigahertz, which is sub-millimeter, to go along with the 86 gigahertz and the 230 gigahertz measurements. And measuring at these different frequencies tells you even more information about the image. And so in 2017, measured at 230 gigahertz, 8 stations at 6 sites. 2023, we've now gone up to 345, doubled the recording rate, 12 stations at 10 sites. And they're also trying to regularly monitor this on weekly scales where we can, given the fact that we don't have the telescopes full time and have to borrow them for a few weeks at a time. By going to these different frequencies, you can think of each frequency as sort of a different color, if you will, of radio emission. So by going from 3 millimeters to 1.3 millimeters wavelength to 0.87 millimeters, and adding new telescopes like the 37 meter, about 500 feet from me right now at Haystack, and adding Owens Valley and adding the AMT, which is down in South America. And now we're going up to 128 gigabits recording. The faster we can record, the more information we get about these particular emitting objects. And so then you can actually access, we'll go through this, multiple scale structures, and you can start measuring even more detail. And you'll notice that on the right-hand side, the smaller wavelength gets you more resolution and more detail compared to the longer wavelength, which has a little bit more of a blurring. So this is where we would like to be able to go to orders of magnitudes higher dynamic range and broader scale imaging. Where to go beyond this even? Well, there is an intriguing feature of the black hole that we still can't measure. And I'll describe that as one of the last things I'm going to do here. So here we go. Let's make sure that I didn't start, did it? Oh, wait a minute. Let me click on that. Come on. I know this is going to work. Ah, this is terrible. This should work. Well, I'll try to describe it to you in words. So there we go. This is light, direct light that's going around the black hole just once and being bent. And it forms the familiar photon ring. I mean, the familiar ring that we've been looking at, right? The orange donut. That's light that's passed by the black hole once, but it doesn't have to just pass by the black hole once. It can orbit a black hole several times, 2, 3, 4, 5 times before getting kicked out and going to us. And what it forms is a narrower thing called the photon ring, an even more stringent test of general relativity. If one could get an image sharp enough to measure the photon ring, you're now measuring even more properties of the black hole. To do that, you need an interferometer, you need phase information. This is why you can't really do it optically, because you need amplitude and phase. If your job is to measure that ring to see how thin it is and what distance it is, and again, to use general relativity properties to tell you even more about what the black hole is, you can actually just have a baseline. A single baseline can measure that ring property. But the difficulty is that maybe you aren't on the planet anymore measuring it. And if you can measure that photon ring, you can actually quantitatively measure how fast the black hole is spinning. You see that little sort of speedometer gauge there? As the black hole goes from not spinning to spinning, you will notice that the ring begins to offset itself from the center of the normal event horizon shadow. The farther that ring is moved off center, the faster the black hole is spinning. And in fact, if it gets spinning really fast, it even gets distorted. Notice that flat part of the ring on the left-hand side there. So if you can leave the planet, you might get even more resolution by making your interferometer arm longer than the diameter of the planet, and you might be able to try to resolve that ring. And this is, I'm not going to go through that. This is how interested the community is. This is the number of publications that mention both the black hole and photon ring from, I think, APJ, the Astrophysics Journal. Notice the interest in the photon ring. It's basically exploding. Exponential growth in the number of people who are interested in measuring that photon ring. And this is the first results. That first image came out in 2019. And you may know that fields every 10 years go through something called the decadal survey, where they decide what should we be measuring in the next 10 years. Well, that Astro 2020 decadal survey hit just about the same time that the black hole images came out, and suddenly, boom, everybody wants to know about the photon ring, not just the black hole image that we've been measuring. And so this is where we're going. The Smithsonian Center for Astrophysics is leading a multi-institution consortium. Haystack is part of this, to get a measurement arm off the planet, to put a 3.5 meter telescope in a medium Earth orbit. It's actually something called a geosynchronous transfer orbit. It's what normal satellites go through on their way to being geosynchronous satellites, except for you leave this highly elliptical orbit. And as it gets farther away from the planet, the baseline gets longer and longer and longer. And so you can notice the little thing that says there's the ground only one, and then there's the one at ground plus space. You can start to resolve the photon ring. That would be beyond the angular resolution of the one from the ground, and that would literally be the highest angular resolution image anyone has ever made, ever. And the idea here is that, as I said, you can gauge the black hole spin, which is another very key quantity for how it interacts with its environment. This also increases your sensitivity to the point where you can study dozens of black holes, not just the couple that we've been doing so far. It leverages billions of dollars of ground infrastructure in the telescopes that are already on the ground. And it tracks the explosion that I showed you in papers and community interest in the photon ring. And so the idea is that next year, there's a small mission explorer, a NASA proposal that's being assembled to try to see if we can advance this to the point where sometime in the next decade, you could fly a telescope in low Earth orbit or medium Earth orbit, geosynchronous transfer orbit, and get the extra resolution that you need to not only get the normal image, but also to get the photon ring. And there's, again, the goals that I just told you about. This is what you have to do. You have to measure way up at greater than 100 gigahertz radio frequencies. You have to be at least 30,000 kilometers or 5 Earth radii away from the planet. And you need a very high-speed optical downlink of at least 100 gigabits a second from that distance. Believe it or not, laser communications are now getting to the point where you can put that on a satellite and get that level of data continuously down to telescopes that are the ground terminals. So it's becoming possible. So the last thing I want to leave you with is if you go home and you turn on your smart TV and you search on Netflix something called Black Holes, The Edge of All We Know. You can watch that on Apple TV or YouTube or Google Play or Xbox or Netflix. And there's some interesting stuff there. You can also go to blackholefilm.com. And that is where I would like to leave this. Hopefully that was interesting enough to you that you might want to go watch the documentary and watch for more images in the future. So you're all very patient because I haven't heard too much, or at least I've left you all behind, hopefully not. So thanks a lot. And I'm around to take questions. So I will come out of what I'm doing right here.
Well, thank you, Dr. Erickson. So if anyone has any questions, I mean, now's the time. I actually have one.
Sure.
So I understand the amount of data that was collected from the array, and
Right.
looking at these two samples, M87 and Sagittarius A, how much time was spent on collecting the data? And then, when you moved up and you added additional telescopes and built out that array, and you were able to then go to higher frequencies, did that have any impact on the length of data that was taken, or the amount of time, or was it basically, the same amount, or was it extended?
Well, okay. So every new telescope that you add means that you can now form pairs with all the other telescopes that are already in the array. So if you think about it, it's a combinatoric process. If I have 4 telescopes and I add a 5th, I can form 4 new baselines. If I add a 6th, I can add 5 new baselines, and it starts exploding. So the number of time correlations you have to do gets more and more as you add more telescopes, and it kind of runs away from you. So what really happened was the processing takes a lot longer, but fortunately, we're able to keep up and reduce that somewhat by the fact that the correlator keeps getting faster.
Okay.
So in some sense, but you chew on this stuff for quite a while. And what you do is you do your correlation, and then the calibration process, which is the place where you're trying to reject all the noise, all the signals that are not the black hole you're looking at, try to very carefully amplitude and phase calibrate that. That process gets harder and harder as you add more data and you observe at more frequency. So some things are getting harder, even as some things are getting easier. The correlator itself, if you were to look at it, it's like looking at a bunch of racks, server racks of computers, right? It's a software correlator. About 15 years ago, we transitioned from being hardware correlators, where you did the correlators in special function ICs, to doing it on a Linux cluster.
Okay.
And so it's a software correlator. But the thing I also like to point out when people tour the observatory and they see the correlators is that, look, it may be boring, okay, but that's the instrument. The instrument is inside the computer. When the two data from 2 different telescopes are brought together and the data is pattern matched to figure out the part of the signal that's the black hole, and then the other, throw everything else which was measured at one telescope, but not another one, which can't be the thing that they were both looking at. So in some sense, one telescope measuring something is not an instrument. It's the combination inside the telescope. So when you look at the cluster, you can point to somebody and say, that's the instrument. And they have to think about that for. But then they realize it's that processing. It's that bringing together of information. So earlier in the presentation, I pointed out that this is so much data that you literally can't, the internet 2 is not even close to being fast enough. You put it in boxes and you fly it in planes, because per unit clock time, that's still the fastest way to get data. But the data has to come together in one physical location in order for you to be able to do the correlation. So in some sense, only when the data is brought together and correlated does the instrument start working. So it's like an instrument in software. It's a little weird, but that's the way to think about it.
Yeah, so I mean, the Linux, so as this basically the correlator can be seen more of like a Linux cluster, shared compute resources in order to be able to process the information.
That's right. And the idea is that it's paired with an extremely fast reading bus, because you have these sleds of 8 drives each. And the idea is you You don't want to be IO bound. You want to be able to read that in as fast as you possibly can.
Mhm.
So there's some magic about making sure that the drives keep on
That's gotta
feeding you
be
data as fast as
that's gotta be
possible.
flat. That's gotta be flash drive technology. So,
It's still spinning media.
still spinning disk. Wow.
Yeah, because of the cost is still prohibitive to make sure that all of them are replaced with SSD just due to the volume of data. We'll either get to SSDs in the next few years, or we will leapfrog that technology and go to something else like magnetoresistive memory or some other kinds of silicon device. We're not sure, but at the moment, it is literally still spinning drives put in a box and shipped back.
Okay.
Believe it or
Wow,
not.
that's interesting. Okay.
Yeah.
Thank you.
Anybody else?
Anyone else have any questions?
I
That's
noticed
a quiet.
the array seems to be based mostly in the Western Hemisphere. Is that
Yes.
by design or by coincidence?
Well, okay. Hang on one sec. The way I like to think about this is that because this array is not dedicated to the Event Horizon Telescope, this is time that is scheduled on existing radio telescopes, okay? So there's typically a period in April where they're all kind of told to participate in this campaign. So the analogy kind of is you use what you've got. So these are the telescopes that are at least at or above a certain radio diameter, so at or above sensitivity, and that have good enough clocks so that you can coherently measure something and on a timestamp that is synchronized around the planet, okay? So if you can, so the telescopes you see meet those criteria. But the nice thing I like to think about is that it's kind of like, imagine if every day you went out to drive your car and you had to assemble it again from random parts before you could drive it down the highway. That's what you're doing. Every time when you get the telescopes back, one of them is misconfigured in a way that you don't understand, because this is such a precise measurement that people don't necessarily, I mean, a gremlin may have shown up and it's like whack-a-mole. The next time you measure it, some other telescope, and your job is to figure out where the problem is. Maybe the clock is drifting on one of those recordings, and your job is to figure that out and correct it. So it's a bit of a detective story. And every single time they measure, it's a different problem. If we had a lot of money, we would buy a bunch of telescopes that were dedicated to this and put them in various places. But I'm afraid science funding is not even close to being good enough for us to do that. So we make do with what we have. So to your question, yes, there's a lot that are concentrated in the Americas and the Western Hemisphere, you know, the ones out in Hawaii. The South Pole adds a nice baseline. That one is the most difficult to deal with because there's one ship a year that does the transfer. So you actually take your data and you have to wait 4 to 6 months for all the drives to get there on the ship from the pole, South Pole Telescope through Christchurch, up through the Atlantic and back here to Haystack. And you don't know the condition of your data until you open the crate when it's gotten here 6 months later. So that's usually the last station to arrive. Other longitude sectors like Asia, like Indonesia and what have you, maybe someday will join the telescope array. We hope so. But at the moment, the EHT is trying to use pretty much every capability that they have on the ground. Someday, maybe more.
Nothing in Australia.
Not at the present time, and I'm afraid I can't tell you exactly why that is, but in terms of, remember, these also have to have capability given frequencies like 86 gigahertz, 230 gigahertz, and now 345 gigahertz. Those particular frequencies are also chosen because they are in windows where the signal will come through the planet's atmosphere. The water vapor in the atmosphere highly absorbs millimeter radiation, except for in certain bands. So in some sense, you have to pick the windows. And so the telescopes have to be observing in these particular windows if they're on the ground. And you could put the whole telescope array off the planet, but that has its own problems. You can see how much difficulty it is getting one telescope off the planet, much more or less, you know, never mind a whole array of them. And the telescope that we hope to get off the planet is only 3.5 meters in diameter. So what's that? about 10 feet, maybe, or something like that. Some of the telescopes on the ground are 18 meters in diameter, 30 meters in diameter, and nobody's putting that size telescope in orbit anytime soon. So in the sensitivity sense, the ground telescopes are really the anchor here. They are providing you a lot of the sensitivity, while the thing that's going to be in orbit is providing you the angular resolution. And you combine those two and you get the best of both worlds.
They have to be in the driest parts of the Earth, I imagine.
Water vapor is a killer. And in fact, there's a water vapor radiometer next to every telescope that's measuring the columnar amount of water vapor. And if there's too much water vapor, you can't observe that day. So you may have the telescope for 3 weeks, but in that 3 weeks, depending on the site, you could have some good fraction of the days you can't observe at that particular telescope because there's too much water. That's, for example, a particular problem here in Massachusetts, where there are a very few days in late February where it's dry enough in the winter that you could actually make observations at these frequencies. We're not the best site for that. One of the reasons why the telescope hasn't really been added. But the Atacama Large Millimeter Array, ALMA, up at 15,000 feet in Chile, is a very good site. And that's one of the most sensitive arms in the Event Horizon Telescope for that reason, because they don't have as much water vapor up there.